Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at another problem regarding thermodynamics. This time is a problem that involves a bit more complex thinking, but nonetheless it's a great problem to relate everything we've talked about so far. This is a problem by UNSW, and it reads like so. A vertical piston cylinder assembly contains a gas which is constrained by a frictionless piston with a mass of 150 kilograms. During a 3-minute interval, a resistor within the cylinder receives a current of 8 amperes from an external battery at 6 volts. The heat transfer out of the gas is 5.8 kilojoules, and the increase in the internal energy of the gas is 2.4 kilojoules. The area of the piston is 0.003 meters squared, and the atmospheric pressure acting on the outside of the piston is 100 kilopascals. Calculate the distance the piston moves and the efficiency of the process, where efficiency is given as a useful output divided by the total input. Okay, so a lot of things, right, to begin with in the analysis of this problem. We're talking about a piston cylinder device. Very common, we see it all the time, and it has a gas inside. And note that they just say a gas, they don't say which gas. This is air, this is nitrogen, this is oxygen, I don't know, this is helium. So that's an indication that you don't really need to know. We're not going to use any tables. You're not going to need the universal gas constant for a specific type of thing. You're not going to use C sub P, C sub V's. It's a gas, right? We don't have more information about it. And it's a frictionless piston. That's, pretty common in these problems. We don't have to worry about any energy being lost due to friction. The mass of the piston is 150 kilograms. And then there's the new part here, right? Which is there's an interval of 3 minutes with a resistor. And then basically what this is doing is telling you that there's an external source of energy that's supplying energy to our system. And this energy is given in the form of electrical energy. And we know that, power, watts, is just amps times volts. So if I multiply 8 times 6, I'm going to get 48. That's 48 volt amps, which is the same thing as 48 watts, right? Watts, though, is a unit of measurement of rate of energy, right? So power, rate of energy. And I'm giving the interval through which this power is being supplied, 3 minutes. So if I multiply this time by this rate of energy, I'm going to get the total amount of energy that was given to my device, okay? Then we know that this gas loses 5.8 kilojoules to the environment in the form of heat, and that its internal energy increases by 2.4 kilojoules, right? So think about it. Think about what they're saying. They're saying that, we have this device. I'm going to draw it the way we always draw these piston cylinder devices. Here's my piston. Okay, I know that this guy happens to have 150 kilograms, and I know that we happen to have a gas inside this system here, right? What is acting upon this gas? Well, we have the weight of the piston. It's quite a heavy piston. And we also have the atmospheric pressure, right? This happens to be 100 kilopascals, and this mass here happens to be 150 kilograms. So what is acting upon the gas? Well, both the atmospheric pressure plus the weight of the gas. So if I want to know what is the pressure of the gas, I can do, okay, the pressure of the gas, the pressure that's, keeping this piston from compressing this gas completely, is achieved at the time that my pressure is in equilibrium. So that means that the pressure of the gas needs to be the pressure external, or atmospheric in this case, plus the pressure due to the weight of that piston, right? Which is just obviously the weight of the piston times gravity divided by the area, all of which we have. Okay, and then we have the different thing here, which is, a electrical energy input, right? So basically what's happening here is we have, let me do in 2 stages so that this is less confusing. We're going to have our state number 1, which is a state in which it's receiving energy from the battery. Stay there. Okay, and then from state number 1 to state number 2, we have the loss of heat, and we also know we have a gain in delta U, because delta U increases by 2.4 kilojoules, right? So here we don't have a battery anymore, because this battery only lasts for 3 minutes. Okay, now, how much energy is being given by the battery? Well, we talked about that. That's going to be the power given by the battery is going to be volts times current, volts times amps. And the energy, I just need to relate that to the time. So basically it's going to be 6 volts times 8 amps times 3. But as you recall, watt is joules per second, so we need this in seconds, not in minutes. So I'm going to multiply by 60, so we get this in seconds. So I'm multiplying minutes, and then I'm multiplying that by seconds per minute. Okay, so therefore I'm going to get volts times amps, that's watts, times seconds, that's joules. So I get that the total amount of energy that this guy receives is, what did I calculate here, 48 times the 3 times 60, that's about 8.64, already converting into kilojoules instead of having this in joules. Okay, so this is the amount of energy it's, the external source is giving to our gas. Our gas, on the other hand, is taking this like so. It has a 8.64 kilojoule of energy to play with, and it uses it like so. 2.4 goes to the internal energy, so it increases its internal energy by 2.4 from here to here. 5.8 is actually lost in the form of heat. So for it to be able to expand, and expanding, it's able to, push this piston upwards. For it to be able to expand, it only has so much energy left to use in the form of work. How much energy is that? Well, that will be the original 8.64. That is what it has to play with, minus what it lost in the form of, not lost, but used, I guess, in the form of internal energy, right? To increase its internal energy, minus whatever was lost, in this case, less loss in the form of heat. And then we're left with only, this is all kilojoules, we're left with only 0.44 kilojoules. So out of all that energy supplied by the battery, only 0.44 actually were used or could be used by the gas to do work and expand the piston and push the piston upwards. Okay, and note that work was used for the expansion, and the expansion was isobaric, right? Why is that? Well, it's a frictionless piston, and therefore what happens is, as it gains a little bit of energy, it pushes out up this guy a little bit, and then we reach equilibrium again. Then we push it a bit again, push it a bit again, and so on and so forth. So it's safe to assume that the pressure remained constant the whole time, and the pressure in this case is the pressure of the atmosphere plus the pressure of the weight of the piston that we haven't calculated, but we can. That's going to be simple for us to do. That's just 150 kilograms times, call it 9.8 meters per second squared, acceleration of gravity, and then divided by the area, which is 0.003 meters squared. Okay, unit wise, let's check before we do something silly here. We have kilograms times meters per second squared, and this is the same thing as a Newton, and then we're dividing that by meters squared, and this is the same thing as a Pascal. So if I want to keep this in kilopascal, which makes sense because I'm trying to sum with kilopascals, I need to divide the whole thing by 1,000. Okay, so dividing by 1,000, this gives me a grand total of pressure being equal to 590 kilopascals. Okay, note that most of the pressure is actually due to the weight of the piston, not due to the atmosphere. All right, so we have 590 kilopascals pushing down on the gas, and the gas pushing back into all these forces being applied to it, and it needs to do some work. We know that work is the integral of PdV, and we know that this is a quasi-equilibrium system or situation, and therefore this pressure is pretty much constant, right? If the pressure is pretty much constant, then it can leave the integral, meaning that this is just going to be the integral of dV, which is just pressure times the delta V. Okay, what up next? I'm looking for, the distance, okay, the distance. Now, note that the distance that it moves, right, we can look at this drawing here, so whatever this distance that I've drawn here is, the distance that it moves, distance d, is related to the volume, because if it moved by distance d, it has moved a given volume, v, right? And this volume is simply the area of the piston times that distance, right? So the delta v that moved was simply the area times the distance d. The area we know, the delta v we have an equation for, and now the d is what we're looking for. So if I go here and substitute this, we can have, so work divided by my pressure will be equal to my delta v, and my delta v is equal to my area times my distance. That means that if I'm looking for my distance, all I need to do is grab the work, divide it by the pressure, and divide this whole thing by the area. Okay, all things that I have. So this is 0.44. This is 590, 90. And this is 0.003. Okay, if you want to do it in steps, you can do it in steps 2. You can get these two guys here by themselves. That's going to give you that the delta V was about 7.45 times 10 to the minus 3. And then you can calculate the distance. But if you want to go ahead and skip steps, we can do this. We just need to ensure that all the units are, they make sense. So we have kilojoules on the top there. Then we have kilopascals on the bottom. And we have meters squared also on the bottom. Kilo and kilo. Joules per pascals, that's going to be meters cubed per meter squared, that's going to be meters. So our answer is going to be meters, which makes a lot of sense. And with that, we find that the distance moved was 0.248587, keeps going. So we can go ahead and approximate this to 0.249 meters. All right, so that's the distance that the piston traveled upwards as this gas is grabbing this energy from the battery and applying it to do useful work. But it's only a fraction of it. And indeed, the next part of the question is asking us what fraction, how much was actually used in the form of useful output. Well, what do you know? Out of all that energy that was given, and that was the 8 point something that we calculated, 8.64 kilojoules, 8.64 kilojoules was the total energy available for this gas to do some work and therefore push the piston upwards. Only a mere 0.44 were actually useful work. The other, the majority of the energy was actually lost in the form of heat. And then another good chunk was used for the gas to increase its internal energy. And only 0.44 were used for it to do useful work. And then this turns out to be about 5%, 0.05. So only 5% of the energy it received from the battery were put to good use, if obviously the idea was to push the piston, right? So if this is a piston cylinder device and you want the piston to move, then you want as much as you can the energy to be used as in the form of work. But in this case here, only 5% were used. All right. So, there's nothing like super hard in terms of the math of it, but obviously all these little steps, understanding how this is the energy being supplied, understanding how, we have a certain amount of energy And then because delta U on a closed system is heat and work, because we know how much delta U increased by, how much heat was lost, therefore the only thing that's left is work, and therefore only little work was done. And then obviously relating work to the delta V, relating delta V to the distance d. There's a lot of little steps that can get you. So please go back and do it on your own. If you have any questions, as per usual, just leave them down below in the comment section. And if this video has helped you out, consider giving it a like, and we'll talk soon.